Hello everyone, Dr. Somicham here. Today we are looking at one of the most foundational tools in statistics, the histogram, a way to take lots of numbers and turn them into something meaningful and visual. In education, we collect a lot of data: reading scores, attendance rates, graduation rates, classroom noise levels, screen time, behavioral referrals, you name it. But raw numbers alone don't tell the story. We need tools that help us see patterns. And that's where histograms come in. Let's begin with a common challenge in school research. Imagine we're studying student reading fluency scores across a district's third grade classrooms. Let's say we have oral reading fluency scores measured in words correct per minute from 1,200 students. At first glance, that's just a long spreadsheet, but we want to know, how are students performing overall? Are most students clustered around the typical range? Are there students performing far below or above the range? So we create a histogram. A histogram is like a bar graph, but it groups values into intervals or bins along the horizontal axis. In our case, each bin might represent a 10-point score range, like 0 to 9, 10 to 19, and so on. The height of each bar shows how many students fall into the score range. Once the histogram is built, we start to see the story. Maybe most students score between 80 and 100 WCPM, words correct per minute. A few are in the 40 to 60 range, and a handful are scoring above 130. Now we can describe the shape of our data, whether it's symmetrical, skewed, or has multiple peaks. Let's say the distribution is skewed to the right. That means most students are clustered toward the lower scores, and fewer students are achieving very high fluency. That might signal a broader instructional issue or inequities in reading support across the district. Now, suppose there are few students with scores under 30 or over 160. These are outliers, data points that fall far outside the overall pattern. Outliers in education are always worth a closer look. The student with 160 WCPM may be an advanced reader, or maybe the teacher made a scoring error. The student scoring 25 might be a recent English learner or a student with an IEP. In qualitative terms, we might call this disconforming data. It challenges the dominant narrative and raises new questions. Let me shift to a different example. When students complete their online assignments, let's say we're analyzing a high school's learning management system data to track when students submit work. We collect timestamps from 2,000 assignment submissions over 2 weeks. Now we want to know, when are students most active? Does assignment submission spike before midnight? Are there differences on weekdays versus weekends? We build a histogram using hourly bins. The x-axis shows time of day, from midnight to 11 p.m., and the y-axis shows number of submissions. What we might find is a clear cluster between 8 and 10 p.m., the late night submission rush. That tells us something important. Students are doing homework later, possibly after extracurriculars or jobs. And if there's a surprising spike at 6 a.m., that's another kind of outlier. Why? Are students submitting last minute before school starts? Are there access issues at home that only get resolved in the morning? These outliers aren't just statistical, they are human. They connect to schedules, well-being, and workload. One more critical point about histograms: the bin size matters. Let's go back to those reading fluency scores. If we use very wide bins, say 0 to 49, 50 to 99, 100 to 149, then we lose the nuance. It just shows us general trends. If we use very narrow bins, however, say every 2 points, we may get a jagged graph that's hard to interpret. So, we strike a balance. Choose bins that show enough detail to see variation, but not so much that the data becomes noisy. In education research, especially with small samples, the bin size can make or break your histogram's clarity. Let's finish with one more education-specific example. Weekly earnings of first-generation college graduates 1 year after graduation. Let's say we're analyzing wage data from a state grant program. We build a histogram and immediately see it's right skewed. Most graduates earn between 500 and 800 per week, but a few earn 1,200 or more. This tells us two things. The mean salary may be misleading. It gets pulled up by the high earners. There may be important differences based on major, job sector, or region that require further disaggregation of the data. Now you're doing real data storytelling, not just showing a distribution, but interpreting it in context. To add another layer, let's consider attendance rates in a middle school. Suppose we have attendance data for 500 students over a semester. We want to know, are there patterns in attendance? Do certain days have higher absentee rates? We create a histogram with bins representing each day of the week. The x-axis shows days, Monday to Friday, and the y-axis shows the number of absences. What we might find is a peak in absences on Mondays and Fridays. This could indicate students are extending their weekends. If there's a spike on Wednesdays, it might suggest midweek fatigue. These patterns can inform school policies or interventions to improve attendance. Let's wrap up with some key points. Histograms are foundational for understanding distributions in educational data. They help us visualize patterns, center, spread, and outliers in a way raw numbers cannot. The shape of a histogram can lead to new insights about achievement, access, behavior, and equity. Bin width is a strategic choice that affects the story your data tells. Histograms help us move from what does the data say to what does it mean and why does it matter. For your own research, I encourage you to take a small data set, perhaps from a classroom observation, survey, or district report, and create a histogram. Ask yourself, where is the data centered? What stands out? What questions does this raise? Thanks for being here, and I look forward to seeing you next time.